Okay, in this video we'll be going through the 2017 Mechanics Exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you completed the question or get stuck, unpause the video to see how I go about getting the answer. Two astronauts, Sylvia and Sam, are on a mission to another planet. During their journey, they are doing a spacewalk outside their spaceship. At one time, they're moving freely as shown below in the diagram. They collide and stick together. Calculate the distance between Sam and the center of mass of the system when he and Sylvia are 4.8 meters apart. Alright, so we know our equation for center of mass is x center of mass is equal to m1 x1 plus m2 x2 all over m1 plus m2. Now it wants us to calculate the distance between Sam and the center of mass of the system, and so what we can do is we can set Sam as the reference point, and therefore we can call this x1, and because Sam is the reference point, x1 is equal to 0 meters. And therefore Sam will be our m1, and therefore m1 is 105 kgs. And therefore as Sam is m1 and x1, Sylvia is going to be x2 and m2, and our distance x2 is going to be 4.8 meters, okay? That is this distance right here, okay? And m2 is going to be the mass of Sylvia, which is 95 kgs. So now because x1 is 0, we can just simply cancel out this term, and we get m2 x2 all over m1 plus m2. Now we can plug in our numbers. M2 is 95 kgs times our distance, which is 4.8, all over 95 plus 105. And this gives a center of mass of 2.28 meters. Describe what happens to the center of mass of the system as the astronauts move closer together and then they collide. So assuming no external forces and therefore momentum is conserved, the center of mass of the system will continue to move at a constant velocity. Alright, and you can write that in. Calculate the astronauts' combined speed after they collide. Alright, so we have our situation here. This is our before state, okay, before. And as we can see, Sam's momentum is going downwards, and so we can draw a vector going down for Sam. And so this is the momentum of Sam. And Sylvia's momentum is to the right, so we can draw her momentum vector like so. And this is momentum of Sylvia. And therefore, from this, we can see a resultant vector, which is going to be our final momentum once they have stuck together. And as you can see, we form a right angled triangle like so. And so what we can do is we can calculate the momentum of Sam, and that's obviously equal to the mass times the velocity. The mass of Sam is 105 kgs times his velocity of 1.2 meters per second, that's given up here. Okay, and this gives a momentum of Sam as 126 kg meters per second. And we can do the same thing for Sylvia. Her momentum is obviously, again, mass times velocity. Her mass is 95 kgs times her velocity of 1.4 meters per second, and this gives a momentum of 133 kg meters per second. And so now we can do our Pythagoras, where our momentum finally is equal to square root 126 squared plus 133 squared, and this gives a final momentum as 7 square root 685, or 183.21 kg meters per second. Now in your calculation, I highly recommend you use this value right here to keep whole values. Alright, so now we need to calculate their combined speed when they are stuck together, and to do that we obviously know that the momentum finally is again equal to mass times velocity, and so now we can just rearrange for our velocity, and we get velocity is equal to the momentum finally all over the mass. The mass in this case is the mass of Sylvia and Sam combined. Alright, so we have our velocity is equal to the final momentum. Again, we're going to use this value right here to keep whole values. So that's 7 square root 685 all over the mass of Sylvia, which is 95, plus the mass of Sam, which is 105 kgs. And this gives a velocity of 0.916 meters per second. There we go. When the spaceship reaches the planet, the spaceship goes into an orbit around the planet with a period of 5.46 times 10 to the 3 seconds, at a height of 351 kilometers above the surface. Assume the orbit is circular and the planet has a radius of 5,220 kilometers. Calculate the mass of the planet. Alright, so we know that when the spaceship is in orbit, it's in circular motion around the planet, and in this case the Fc on the circular motion is provided by our Fg, and so our Fg is equal to Fc. Our Fg, as we know, is gravitational constant, big mass, little mass, all over r squared, where the big mass is the mass of the planet, and our little mass is the mass of the spaceship, and this is equal to mv squared over r, and again, this is a little mass, so that's the mass of our spaceship. We can cancel out our little mass on both sides, and we get our gravitational constant times our big mass all over our r squared is equal to v squared all over r, okay? Now we can move this r up here, and we get gmr all over r squared is equal to v squared. This r will cancel out, and we get gm all over r is equal to v squared. Now we are given our r value, because remember that our r value is the distance between the center of mass of the two objects. We know our gravitational constant because it's a constant, and we're trying to calculate the mass of the planet. However, we don't know v squared. However, what we do know is that v is equal to distance over time, okay? And when we're in circular motion, the distance that we travel is a circumference of a circle, and so our distance is equal to 2 pi r. The time it takes for us to travel the circumference of a circle is equal to 1 period. And so simply we can plug this into here, and we get our velocity is equal to 2 pi r all over t. And therefore, our v squared is equal to 4 pi squared r squared all over t squared. And so therefore, our gravitational constant times our big mass all over our r is equal to 4 pi squared r squared all over t squared. And so therefore, the mass of the planet is equal to 4 pi squared r cubed all over g times t squared. All right, so now we can simply plug in our numbers. Obviously, we know what 4 pi squared is because that doesn't change, those are just numbers. We know our gravitational constant, we are given our period as over here, and we know our r. However, what is our r? We would have our spaceship over here, and we have our planet over here. We are given how far above the spaceship is above the surface, so we are given this distance right here, and that's 351 times 10 to the 3 meters, because that's 351 kilometers, okay? And we're also given the radius of the planet, so that is this right here, so 5220 times 10 to the 3 meters. And this whole thing is our r value, this whole thing is r. So therefore r is equal to 351 times 10 to the 3 plus 5220 times 10 to the 3, and this gives an r value of 5571000 meters. All right, so now we can simply plug this into here, okay, and we get our mass of the planet is equal to 4 pi squared times 5571000, that's cubed, all over 6.67 times 10 to the negative 11 times our period squared, which our period is 5.46 times 10 to the 3 apparently, yep, times 10 to the 3, and that's all squared. And this gives the mass of the planet as 3.43 times 10 to the 24 kgs. There we go. On the return journey to Earth, the spaceship goes past a different planet. The spaceship's path is shown in the diagram. Explain how the spaceship's speed changes as it gets closer to the planet. So on a whole, when the spaceship gets closer, we lose gravitational potential energy and then gain EK, okay? And when we gain EK, as we know, EK is equal to half mv squared, and therefore the mass of the spaceship isn't going to change. And so if we gain EK, that only means we are getting faster. Our linear velocity is increasing, okay? And also, to visualize this, we know, as we said in the previous question, when we're in circular motion, which we are in this case, right? We're moving in a circle in this case. We know that our centripetal force is provided by Fg. And therefore, mv squared all over r is equal to g big mass, little mass, all over r squared. And then we can simplify this to v squared is equal to gm all over r. Okay? When we get closer to the planet, this r value is going to decrease, correct? And so when this r value is going to decrease, obviously the gravitational constant is not going to change, the mass of the planet is not going to change, and so when r decreases, this only means that our velocity must increase, okay? And so therefore, when we get closer to the planet, our linear velocity is going to increase. Sylvia and Sam's spaceship spins clockwise on its axis and is moving through space. The astronauts can change its angular velocity of the spaceship by firing 2 small rockets that are mounted tangentially as shown. The rockets produce an anti-clockwise torque, and the rotational inertia of the spaceship is 5.8 times 10 to the 4 kg meters squared. Calculate the size of the torque required from each rocket to cause an angular acceleration of 2 times 10 to the negative 2 radians per second. So as we know, torque is equal to I alpha, and in this case, it's going to be the sum of all torques is equal to I alpha, and that just means all torques produced must equal to I alpha, okay? And so as we know, there are 2 rockets producing a torque, and so the sum of all torques is basically the combined torque produced by the 2 rockets. And so we're given the rotational inertia of this spaceship, and we are also given the angular acceleration that we require, and so we can just simply plug it in our numbers. The sum of all torques is equal to 5.8 times 10 to the 4 multiplied by 2 0.00 times 10 to the negative 2, and this gives the sum of all torques is equal to 1160 Newton meters, and therefore, as they are two identical rockets, we can just simply divide this number by 2, and we get the torque produced by one rocket is equal to 580 Newton meters. There we go. The spaceship is rotating clockwise at 0.58 radians per second when the rockets are fired. Calculate the angular speed of the rocket ship after one rotation. Alright, so for this question, we can use the kinematic that our angular velocity finally squared is equal to our angular velocity initially squared plus 2 alpha theta. We want to find our final angular velocity given here. We know our initial angular velocity as it's given right here. We want to find the final angular velocity after one rotation, and so our theta value is going to be 2 pi because that's the amount of angles in one rotation. And we also know our angular acceleration as it's given in our previous question, okay? And so therefore we can simply plug in our numbers. Our angular velocity finally squared is equal to 0.58 plus 2 times our angular acceleration, and our angular acceleration is given as 2 times 10 to the negative 2 radians per second. However, something that might have tripped you up is that the rocket ship is spinning clockwise, and right now we are rotating clockwise. However, these small rockets attached to the spaceship produce an anti-clockwise torque, and so therefore our angular acceleration is going to be negative. And so this is going to be negative 2.00 times 10 to the negative 2 times our theta value, which is 2 pi. And so therefore we can get rid of the square root and square root both sides, and we get a final angular velocity as 0.29 radians per second. Assume that the torque produced by the rockets is constant. Explain what happens to the size of the angular acceleration as the rockets gradually emit burnt fuel. So as we know, torque is equal to I alpha, and we also know that our rotational inertia is directly proportional to our mass times our radius squared. As the spaceship continues to burn fuel, the mass of the spaceship is going to decrease, and therefore our rotational inertia is going to decrease. And so even though the torque produced by the rockets is constant, if our rotational inertia decreases, therefore our angular acceleration must increase. Alright, and you can write that in. Sometime later, the spaceship is rotating freely at 0.45 radians per second, with the rockets turned off as shown in diagram 1. The spaceship's photovoltaic cells are then extended out from the spaceship, causing the rotational inertia to increase by 2.74 times 10 to the 3 kg meters squared. Explain why the period of rotation changes as the photovoltaic cells are extended in diagram 2. Alright, so we know that our rotational inertia is directly proportional to mr squared, as I said in the previous question. When the photovoltaic cells are extended, our effective radius is going to increase. Once again, if you don't know what effective radius means, I go through it in my rotational motions video. That's on my mechanics playlist. And so if our effective radius increases, therefore our rotational inertia is going to increase. And as we know, angular momentum is conserved and therefore is constant. And we also know our angular momentum is equal to I omega. If our rotational inertia has increased, therefore our angular velocity must decrease. And so as our angular velocity is equal to 2 pi all over t, if our angular velocity decreases, therefore our period will increase. And you can write that in. Calculate the period of rotation when the photovoltaic cells are fully extended. So we know due to the conservation of angular momentum, our angular momentum initially is going to be equal to our angular momentum finally. Okay, and we also know that angular momentum is equal to I omega. We were given our rotational inertia, and that's all the way up here, okay? And so we can plug that in, 5.8 times 10 to the 4. We also know our angular velocity as that is given right over here, so we can plug that in, 0.45. And this gives an angular momentum of 26100 kg meters squared per second, all right? And so therefore, if this is our angular momentum initially, okay, and so therefore our angular momentum finally must be equal to 26,100, okay? Now, again, we know our angular momentum finally is given as I omega, and so we can label this as our rotational inertia finally and our angular velocity finally, and that's all equal to 26,100. Okay, we can see up here that our rotational inertia has increased by 2.74 times 10 to the 3, and so therefore our rotational inertia finally is going to be 5.8 times 10 to the 4 plus 2.74 times 10 to the 3. Okay, and that's multiplied by our angular velocity finally. We don't know what that is, and that's equal to 26,100. Now therefore we can rearrange for our angular velocity finally, and we get our angular velocity finally is equal to 26,100, all over 5.8 times 10 to the 4 plus 2.74 times 10 to the 3. And this gives an angular velocity finally as 0.4297 radians per second. And as we know, our angular velocity finally is going to be equal to 2 pi all over the period. And as you can see up here, the period is what we're trying to find. And so therefore 0.4297 is equal to 2 pi all over our period. And therefore our period is equal to 2 pi all over 0.4297. Okay, and this gives a period of 14.62 seconds. There we go. Astronauts need to be able to measure their mass so they can monitor their health. They can do this by being strapped onto a lightweight seat that is attached to a spring as shown in the diagram below. When Sylvia is displaced from the equilibrium, she oscillates in simple harmonic motion with a period of 8 seconds. You may assume her motion is linear. Describe any changes in the size or direction of the restoring force as Sylvia moves away from the equilibrium position in the plus y direction. So this goes back to the definition of simple harmonic motion. The restoring force is directly proportional and in opposite direction to the displacement. And so therefore, as Sylvia moves further and further away from the equilibrium position, the restoring force is going to increase. Okay, but this restoring force is going to remain downwards because she is moving upwards. As we know, the restoring force is opposite direction to the displacement. If she is moving upwards, then the restoring force must be downwards. Okay, and you can write that in. The amplitude of Sylvia's oscillation is 0.12 meters. Use a reference circle or any other method to calculate the shortest time it takes for Sylvia to move 0.08 from her equilibrium position. So we are starting at the equilibrium position, and we want to find how long it takes to move 0.08 meters. So we can call this distance 0.08 meters. And so therefore we can write that on our reference circle, and we can draw in our phasor, draw down a right angle triangle. Again, this distance is 0.08 meters. As we know, the amplitude is 0.12 meters, and so therefore this radius is 0.12 meters, okay? And we have an angle theta right here. We can draw out that right angle triangle bigger to make it easier to work with. So we have theta here, 0.12 meters, and this is 0.08 meters, okay? And now we can calculate our theta. We know our theta is equal to the inverse sine, and that's equal to 0.08 all over 0.12, and this gives a theta value of 0.7297 radians. Again, when you're working with a reference circle, always work in radians. And so therefore, as theta is equal to omega t, our time is given as theta all over our omega. We just found our theta value, so we can plug that in over here, and our omega is given as 2 pi all over our period. And we are given a period over here of 8 seconds. And so therefore, our time is going to be equal to 0.7297 all over 2 pi divided by 8 seconds. And this gives a time of 0.929 seconds. There we go. On the axis below, draw a graph showing Sylvia's velocity versus time, starting when she is closest to the floor. Include the value of the maximum velocity. Alright, so first, we need to calculate her max velocity. We know that Vmax is given as A omega. Okay, this is not on your formula sheet, and if you don't know where that comes from, go watch my reference circle video. And also, if you are confused with our previous question on the reference circle, again, go watch my reference circle video, and you should be good. Vmax is equal to A omega, where our A is our amplitude, and we know that's 0.12 meters, all over our omega, which we know is 2 pi all over 8 seconds, okay? And this gives a Vmax of 0.094 meters per second. There we go. And so therefore on our axis, that is going to be roughly like right here. That's going to be our Vmax, and our negative Vmax is going to be roughly over here, okay? And so we can draw that in. Again, it says we start when she is closest to the floor. And so if we look at our diagram, when she's closest to the floor, that's over here, she's over here, she is going to be momentarily at rest. And so we start at 0 velocity. And so our 0 velocity is right here. So that's where we're going to start. And we also know that 1 period is 8 seconds. And so this graph should show 1 period. Okay. And so nicely, this graph is given in quarters. And so this should be half, and this should be 1/4, and this should be 3/4. Okay. And so after 1/4, we should be up here. And after 3/4, we should be roughly down here. Okay. And so now we can simply draw our sine curve like so, like this, and then up finally like, okay, there we go. If you don't know why her velocity follows a sine curve, again, go watch my reference circle video, or my simple harmonic motion video. I go through it in both of those, why the velocity follows a sine curve. To start the oscillation, Sam applies a vertical force of 4.4 newtons to Sylvia. This force causes Sylvia to move at a distance of 0.12 meters. Describe any assumptions you have made to simplify your calculation. Alright, so there are two ways to solve this problem. The first one being, we know that force is equal to kx. Alright, and therefore K is equal to our force all over our displacement. We are given the force that is applied, and we are also given the displacement of the spring due to that force, and so we can simply plug that in, 4.4 all over 0.12, and this gives a spring constant of 36.67 newtons per meter. Okay, and then from here we know our period is equal to 2 pi square root m all over our spring constant. We know our period from before, and that's 8 seconds. We are trying to find the mass, and we just found our spring constant. And so we can just rearrange for mass, and we get our period all over 2 pi is equal to square root m all over k. And so therefore our period all over 2 pi squared is equal to m all over k. And therefore our period all over 2 pi squared times our spring constant is equal to our mass. And so therefore our period of 8 seconds all over 2 pi squared times our spring constant of 36.67 is equal to our mass, and that gives a mass of 59.44 kgs. And for this method, the assumption that we're going to make is that the mass of the seat that she is sitting on, because remember, she is sitting on a seat, we are going to assume that this mass is negligible because it says over here that the seat is lightweight. And we are also going to assume that the mass of the spring is also negligible, okay? The second method for this is using conservation of energy. And so the assumption for this is that energy is conserved, okay? We can see here in this depiction that we go from maximum EP right here. So this is maximum elastic potential energy. And once we get to the equilibrium position, which is roughly over here, we're going to have max EK. Okay, so this is max EP over here, and then max EK. And so what we can say is that our EP max is going to be equal to our EK max due to conservation of energy. Okay, so we know that EP is equal to half kx squared. We know that F is equal to kx, and therefore K is equal to F all over x, okay? And so now we can simply plug this into here, and we get half F all over x times x squared. This x will cancel out with this power, and we get half times our force times our x, and that's equal to EP. Remember, we are given a force of 4.4 newtons times our displacement, which was 0.12, and this gives an EP of 0.264 joules. Okay, and so therefore we know our EK is going to be equal to 0.264 joules, okay? And we also know that our EK is equal to half mv squared, where in this case our v squared is going to be our v max. We calculated our v max in the previous question, and that's going to be 0.094, and so therefore 0.264 is going to be equal to half times our mass, which is what we're trying to find, times 0.094 squared. And therefore 2 times 0.264 all over 0.094 squared is equal to our mass, and this gives a mass of 59.44 kgs. And as you can see, we get the same answer in both methods. And with that, we're done. See ya.